Welcome to the Cosmic Pie Podcast, Season 4, Episode 19. I am your host, Wayne Barkhouse.
19. Hi, and I'm Rob Moore.
We are streaming live from the campus of the University of North Dakota. Lots of things going on this time of the year, Robert, because we're heading into that beautiful summer season.
Yeah. It's also smoke season, Canadian wildfire season.
Hasn't really started yet. I haven't noticed it.
Started yet, but...
Be on the lookout, right?
Right.
Now, we do have a live chat feature that is running, so if you have any comments or questions you'd like to ask us throughout the podcast, please use that option. Robert?
Yes.
Our disclaimer.
Well, that means the opinions and everything expressed in the show are those of myself and Wayne. They do not reflect. Wow.
Or refract.
Refract the opinions of the University of North Dakota, the Department of Physics and Astrophysics, or any other entity. It's just us, folks.
That's it. And I guess up front, let's let people know what's going to happen next week.
I don't... Oh, right, yeah.
Right. So next week, which would be May the 19th, next Tuesday, we will not have a podcast. And I can just hear the universal groan. Oh. And the reason for it is because it is my 25th wedding anniversary. Yay!
That's a good thing to miss for.
Right. So we will have a podcast the week after that. So that's like May 23rd, I believe.
No, May 26th.
May 26th. Oh, look at that. I got my wedding anniversary on my mind. You see, I forgot about everything else.
You're already ahead of the game.
And the other thing is, on May 26th, we will have a guest. You want to say a little hint about our guest? Who it is?
Well, she got her start with NASA working on the Voyager mission. Voyager 2, I think it was. And then moved into Cassini. Helping out with Cassini, and was working on Europa Clipper when things got a little tight in the budget. So,
yes, so she'll be very
Trina Ray, and she'll be joining us on the 26th.
Right, so that's going to be really interesting. So I can't wait to if you like, hit her with a bunch of questions about what it was like to work on the Voyager 2 mission, because that's one of the most, in my opinion, most successful robotic exploration of the solar system that we've launched.
Oh, yeah.
So, I mean,
wonderful mission.
For those who don't know, that's the one that was launched. There was Voyager 1 and 2 back in 1977. And then they did the first real good reconnaissance of Jupiter and Saturn, and the first reconnaissance of Uranus and Neptune with Voyager 2. And, of course, since that time, we had New Horizon back in July of 2015 fly by the planet Pluto. And so in that sense, the traditional solar system with 9 planets, today it's non-traditional if you like, with 8 planets. We leave out poor Pluto. And we've had that discussion in the past and no sense of doing it today. But we've actually flew by all of the planets in the solar system since 2015.
But it's time to go back to Uranus and Neptune. It really is.
It's a good thought. I mean, Uranus, for example, as I said, we flew by the planet, but so how much time do you have to make detailed observations about the planet in the moon system? At best, just a couple of hours.
Are the rings? Are the it's not cyclonic. The winds on Neptune.
Yeah.
Those are the highest wind speeds that have been recorded in the solar system.
Yes, for sure.
So.
Yeah. And we can take some images, of course, of Uranus and Neptune with like the Hubble Space Telescope or with the James Webb Space Telescope, but they're certainly not as good as what it would be if you're actually there flying by.
Right. So.
And the other thing is, and these planets are, they have the extensive moon systems, like miniature solar systems in their own way.
Right.
And so there's a lot of work that needs to be done with those.
And Uranus is on its side. Its axial tilt is horizontal, parallel to the plane, essentially, of the solar system, instead of nearly perpendicular to it. Just lots of things. Yeah,
that's for those who don't know. So, when you think of the rotation axis of Uranus, it's not as you expect nearly perpendicular to the plane of the solar system. It's actually pointed more towards the sun, not exactly, but close. It's almost as if something hit it and it fell over to its side.
Right.
And of course, people speculate that might have happened in the very early solar system. But who knows, right?
Who knows?
I mean, there's a lot of work, and today we can do. One way to find out is detailed simulations to see if you can kind of reproduce all of the physical attributes of the, of the planet itself. But
It'd also kind of be neat to have it hit by something like Comet Shoemaker-Levy 9, so we could do the analysis of the seismic waves set up in the atmosphere and things like that. But
yeah, I'd settle if we're going to Uranus, which is, as we know, it's on NASA's sort of wish list, that they would like to have an orbiter going around the planet so it can stay there for a while, let's say for several years. If you're going to take the time and effort and the money to get to the planet, then you may as well stay a while.
Right.
And in that case, maybe you drop an atmospheric reentry probe into the planet.
Or
and,
two, or I don't know.
and you can make direct in situ, as they say, meathements of
Sniff
the
atmosphere.
Yeah, of the properties of the atmosphere. So what is its chemical composition? What are the pressures? And how do those things change as you fall in towards the center of the planet itself? Until eventually, of course, whatever you send in will get destroyed from the extreme environment and pressures and so on.
Pressure, temperature.
Yeah.
Yeah.
And of course, there's other talk of doing the same thing, but for Neptune. So you can have an orbiter going around Neptune and also have an entry probe as well. And then eventually, hopefully not too distant future from now, you can imagine we have little landers that would land on some of the major moons of these planets as well.
Right.
And that would be kind of interesting to see that. And, the way I would approach it, if you could do it, is do it on the cheap. And therefore you can make a lot of them.
Okay, yeah.
And if you send some of them to a risky environment, because at first you'd want to I want to send it somewhere where it's level, like a nice flat region.
Right.
But from geology point of view, that's not always the most interesting place to go on these objects, right?
Right, because safe is usually not interesting.
So let's send it into some kind of a crevice or the bottom of a crater or somewhere where the surface has been maybe, gorged up by an impact or something, and try to get a better measurement of stuff that lies underneath typically, but has now been brought to the surface because of an impact of some object or something.
Yeah.
That's what you want to do, right?
Let's look at Mimas. Let's look at some of these Enceladus, some of these other moons.
And, use our technology, with drones. Just
Enceladus is Saturn, never mind.
If you do a survey of how are drones being used on the Earth today, the vast majority of it would be for warfare.
Right.
And that's unfortunate, right? We have this really great technology that can be extremely useful.
Yeah.
So imagine you could develop, you could think of all kinds of things, but something that just came to imagine that you could deliver life-saving material to firemen that are trapped inside of a large forest fire and there's no other way to get to them. And you can drop the material right in front of them by their feet. And you can, use a drone to do that. Maybe the drone gets destroyed, but who cares, right?
Right.
They provide life-saving, maybe those tents that you go into when the fire sweeps by, to try to save people's lives. There's all kinds of things you can think of, more than dropping bombs on people. You see what I'm getting at?
I'm right there with you.
Use them for a tool of good things, not warfare. If we can get away from that,
right? That would be nice.
And that same technology, as we'll see later on today, is being pushed in terms of development of landing things on other planets to try to explore regions that are very difficult to get to.
Absolutely.
So it's kind of interesting. But, Robert, let's start all this off by going to one of our very famous planets, and that's the planet Mars.
Barsoom.
Now, Robert, did you ever get a package, let's say, from Amazon? And you're all excited, right? Maybe it's your book. Okay?
Okay.
And you open it up and it's like all shrouded in this plastic material. And so you take off the material and you finally get to your book. And then you notice there's a little piece of plastic that's stuck to the end of your finger and you give it a little shake. And yet it doesn't come off. And you try. In fact, you take your other hand and rip it up and now it's stuck to the other hand.
Right.
And it's like, oh my God, this is annoying, right? So it's electrostatic charge, of course. And you try to wipe it on something to get rid of it. Well, that's what happened to the Curiosity rover recently on Mars.
Except it wasn't static, but yeah.
And it wasn't plastic. So
Yeah.
the rover drilled into a rock. And what happened was, once they stopped drilling, the rock did not drop off the drill bit. In fact, they actually lifted the rock from the surface of the planet. Now, we're not talking about any rock. We're talking about a rock that weighs about 29 pounds, estimated here. And so it wasn't a small little pebble. And normally what happens when you drill into a rock like this, it usually breaks around the drill entry,
Right.
the bore hole, if you like, and it shatters it to an extent where it's easy to extract the drill bit. But in not this case. I wonder if the material of the rock was different than normal.
I would bet just it almost certainly had to have been. It could have been a lot more porous. It could have been a lot more made up of some material that it closed up back around it, kind of like wood does with a drill bit, and why you've got special bits to drill into wood. There's almost certainly this was unexpected behavior.
And it's not like you can leave it there, right? You can't have the rover transversing across Martian surface with a big rock hanging off the side of it. I don't even know from an engineering point of view if we've been capable of even doing that.
Right.
Out of the sort of abundance of caution, they probably wouldn't have liked to move the rover. Yeah, you try everything you possibly can try to get rid of the rock type of thing, right? But eventually it did. They turned on the drill again, and they drilled in further, and eventually it let go. And so they were able to proceed. But the image that you see there is actually the part of the arm from the rover with the drill at the very bottom and the orientation that you see here with the drill bit actually in the rock itself. And the rock is lifted off the surface. So it's like... And they shook the arm, and you envision with a piece of plastic stuck to your finger. How to get rid of this
Even
thing?
worse is styrofoam.
Right. Yeah, that's
Holy
right.
crap.
And that's the stuff that sticks to your clothes, too. You notice, and everything else in your
It sticks to
house.
everything. In your hair, on your fingers.
And it's not like you can call help and say, come over and would you please remove the rock from the end of my drill? And,
Right.
There's nobody there to do that, obviously. So luckily it came up. It's quite interesting. I thought that was kind of a cool sort of thing that happened.
Yeah.
Now, you ready?
Ready.
This is a fantastic view of what we call the Sombrero Galaxy. Now, this galaxy is located about 30 million light years away from the Earth. The interesting thing about it, if you look in the very middle of that hazy sort of spherical-shaped object, you see like a flattened disk that's almost edge-on to us. In fact, when we classify different galaxies, like spirals, for example, this is like a typical, what we call an SA type of spiral galaxy, where it's viewed, aligned to us, or if you like, projected, edge-on nearly. Mm-hmm. And one of the things, when you look at it very carefully near the center, you see that sort of line of dust, really dark, that's on the leading edge pointed towards us. So that gives you an illustration that this galaxy contains a lot of interstellar matter. And what's cool about this image, this is a recent image that was taken by the Dark Energy Camera, DCAM. And DCAM was specially designed. In fact, I worked on the project, the Dark Energy Survey, so I have, an inside track a little bit on this. So this camera was designed to look over a large field of view around 3 square degrees of the sky in a single exposure. And so that's enormous when you think about it.
Right. That is a big field of view.
Yeah, and the idea was to cover a large swath of the sky in the south over a reasonably short period of time, of roughly 5 years. And from that, look at millions and millions and millions of galaxies and so on. You can do all kinds of science, right? Mm-hmm. You can do science from solar system type work, because if you look over a wide field of view, that increases your chance of picking up new asteroids.
Right.
All the way out to the furthest reaches that you can observe different galaxies and quasars and so on and so forth. And to try to get a measurement of, and this is the primary, hence the name of it, try to get a measurement of the accelerated expansion of our universe. And that's the signature of what we call today dark energy. And
right.
So that was the kind of the design of the survey, was to get a good handle, a more precise measurement of the amount of dark energy in our universe. And hence the need then for this wide field of view.
Is that in part due to that study that recently suggested the dark energy quantity or density might not be constant over the history of the universe?
Right. So you're referring to the DESI, the Dark Energy Spectroscopic Instrument. And DESI is a 5-year, and it's been extended, use of the 4-meter telescope at the Kitt Peak National Observatory, just outside of Tucson. And the goal of that project was also to get a good handle on dark energy. And one of the things that they saw in the results using preliminary data, and that's an important word, preliminary.
Preliminary, yeah.
Was that they had evidence possibly, and I'll hint going all around it because we don't know for sure, that dark energy becomes weaker with time. And before that sort of survey was hinted at this possibility, all measurements were showing, and these are measurements with a certain uncertainty. You know, every measurement has an uncertainty. If it doesn't have an uncertainty, it's useless in science.
Right.
And all measurements were showing that the dark energy was a constant, the so-called cosmological constant. That is, whatever value it has in terms of its energy density, at the very beginning of the universe, it would have that value today and going forward into the distant future. Now, with the DESI survey, DESI survey, there was a hint that that was changing. It was getting weaker with time. The full data hasn't been analyzed. It just finished taking all of their data recently, so they're well into trying to crunch the numbers to get a more, if you like, robust result to see for sure if that's indeed the result holds up, the fact that the dark energy is getting weaker with time. But the result from the dark energy survey, so this is a different survey, it's completed, and the results are out there. The papers have been published. And what they show is that now this is a thing in science you have to be aware of. The data source that you have, of course, is what drives your results. Mm-hmm. You change your data source, you can get different results. Now, you can also take results from multiple measurements. And that's what the Dark Energy Survey did. It had published papers based on multiple data sources and how you put the data together. So those data get put together in different ways. For example, you could just look at looking at supernovae results and get a certain result, or you can bring in what we call baryonic acoustic oscillations. So these are technical descriptions of different types of analysis that one can do, and you get slightly different results, which is expected, right? It's expected. Measuring the length of your table as precise as you can with a ruler or tape measure, and then you repeat that again, and you're going to get a slightly different number.
Right. And what we're looking for, though, is numbers that point to the same general answer. So.
Yeah, convergence.
Convergence.
And what the Dark Energy Survey's results are showing is that they agree that there is support, if you like, with a changing dark energy, but it's only, quote unquote, and underline that because we'll talk about it later on in the podcast, it's at the 3 sigma level.
Oh, okay. So
okay.
Still far from a detection.
Right. And for those of you who don't know what we're talking about, when we say sigma, we're talking about Gaussian statistics, and we'll talk about that in more detail a little bit later on today.
Right.
So it's a 3 sigma detection, and what you want in science is at least a 5 sigma. So it's a more robust, if you like, more precise type of measurements that can clearly separate your result from maybe your expectations or the models or whatever you're using, or maybe other people's results from a different survey.
Right.
So the end result of all that is we don't know for sure if the dark energy is changing. But with the final results that will come out here, hopefully in less than a year, from the DESI, the DESI survey, that may point the way. It might hit the 5 sigma limit, and then things become real interesting.
Then things become interesting.
For sure. So we'll see that. But the Sombrero Galaxy, it was imaged recently by the Dark Energy Survey. And the reason why I picked this, number one, it's a beautiful image.
Yes.
And what makes it beautiful, in my opinion, most images taken of this galaxy are taken from the very central region because they're a lot smaller format cameras in terms of field of view on the sky.
Right.
And so all you get really is the central region. But the large field of view of the dark energy cameras allows you to observe not only the galaxy itself, but what's outside in the outskirts.
Mm-hmm.
And the interesting thing about this system is if you look sort of to the bottom and a little off to the right, but mainly, and directly to the bottom of this image, you see almost like a rim-shaped faint feature, like part of a wheel, like the rim of a wheel. And part of it you can see in the bottom, and then when it goes sort of up to the upper left a little bit, it kind of disappears. Now, what we're seeing there looks like what you'd expect if another galaxy actually was gravitationally or tidally disrupted as it passed or orbited the main galaxy that you see in the center of the image. So you're seeing really, it looks like the debris from the existence of a once galaxy that was in orbit around this object.
Mm-hmm.
And
I was just going to say, to me, the problem with that is the Sombrero isn't disrupted itself. Galaxies are massive, so even if it was a tiny galaxy, it should have had a countering effect on the Sombrero.
Now, we do see these things in our own Milky Way. There is evidence for well over 80 of these tidal tails, if you want to call it that, where galaxies existed in the past, but as they orbit the Milky Way, they get gravitationally torn apart by the much larger mass of the Milky Way in that case. And so these are low-mass galaxies, what we call dwarf galaxies, that get disrupted and destroyed. And that could be the same thing here. You're seeing the leftover debris, which means stars. And, of course, in there, and that's what we see the light coming from. And you will also see interstellar matter, and there'll be also dark matter, of course, that will respond to that. But you're seeing the disrupted material from small, low-mass galaxies, and they would not have a greater effect of the large, massive galaxy.
Right, but I would expect some warping of the disk or something,
And there could well be that if you measured it precisely. I can't remember if the Sombrero Galaxy has any type of warpage associated with it. If it does, it's not really pronounced. You can't really see it very well.
Because the reason I'm mentioning that is because there is some evidence that our Milky Way galaxy's disk is warped from the consumption or shredding of these smaller galaxies. So.
Yeah, and since we don't know the exact history of those type of merging that occurred in the past, some of those galaxies could have been, quite massive to begin with, and that could be responsible for the warping, where the much lower mass galaxies really didn't do much to it at all. But who knows? And the way to figure this out, of course, is you do simulations.
And simulations and take better observations.
Yeah,
and
simulations, and more simulations.
Let's get some more spectra to feed into the simulations.
Yeah, and if you actually played around with this image, so this image is available online. You just do a look for a Sombrero Galaxy DCAM image, do a search in Google. You actually can get an image that they have set up of this, so you can actually zoom in. And so you can actually go in, and if you go to the very top, you can actually see almost like a set of horn-like features, which is the orbital paths of the galaxy up on the other side, the top side. And so you can tell there's been more than one, because you got sort of an angle of difference between the plane of the orbits of different galaxies that have existed in the past.
Well, and one thing we do know about galaxy evolution is it's a history of galaxy eat galaxy.
Oh, clearly, yeah. Galaxy interaction is major in our universe.
Right.
In terms of how galaxies get the shape and sizes they have today.
Aren't the Magellanic Clouds in the process of being disrupted?
They are, and depending on who you talk to, it's anywhere from 2 billion to 10 billion years from now, the Magellanic Clouds will become part of the Milky Way. In fact, we call that whole process where a low-mass galaxy gets eaten by a more massive galaxy, we call that galactic cannibalism. And so, like I said, there's like evidence of trails of that happening in the Milky Way, over 80 of them.
Right.
So you can speculate that over the last probably 13 plus billion years of the history of the Milky Way, it's undergoing a lot of these mergers, a lot of cannibalism having occurred, and so on. So it's quite, and of course, if you look at high density regions, like in the center of galaxy clusters, for example, you see all kinds of stuff going on.
Right.
And if you want to go where the action is, that's the places to look. And some of them are quite amazing, these things that you see.
Galaxies blowing through each other, wrapping around each other, all sorts of stuff going on.
All kinds of stuff. So pretty cool. Now, next thing in the news, of course, just a few days ago, we had a test of the engines of the next Starship flight, which is thankfully coming up soon. So it's actually this Friday. At least it was by last night, if they haven't changed it today. It's Friday at 5:30 p.m. Central Daylight Time. And it's the so-called version 3 of the Starship. Now, Starship is extremely important for the overall human exploration of the moon and beyond. And the reason for that, as probably most of you know, this is a SpaceX vehicle, and it's one of 2 vehicles that have been selected for a lander on the moon as part of the Artemis mission. So the other one being the Blue Origin, also have their lander that they're in developing. And Starship is the SpaceX version of that lander. Now, there's been a lot of delay with Starship, and it is pushing the technology. And anytime you push technology, you're going to get a lot of delays. That's just expected.
Right.
The thing is, though, we're on a clock here.
Tick tock, tick tock.
So the Artemis II mission, which we know was finished up a couple weeks back, to go around the moon and come back to the Earth. The next one, Artemis III, is to stay in Earth orbit and test one or more of these landers, one from SpaceX, the other one from Blue Origin. But as we're talking right now, neither of those landers are ready to go. They're testing them. I mean, Blue Origin, I seen some news not that long ago where they're testing various components that will eventually, it's one that was going to be an unmanned lander for the moon. It's not the human-rated version, but it's part of that development process. So they're well on their way working on that, and as we know, Starship is. So this new version is supposed to be more powerful, that they will try launching this Friday, so it's well worth having a peek then if you like to look at those launches, to hopefully everything works well. I'm hoping, not for the sake of the CEO necessarily of the companies, but it's an integral part, whether we like it or not, and I like it. I mean, maybe it's the way to go to get a lot of these rockets developed and by private companies, and NASA would just buy the service. Okay. It has a major impact on the Artemis project and the time frame. When are we going to be able to eventually land on the moon? And those dates will continually be pushed further and further into the future if we have trouble developing these landers. These are crucial components. And we need to work. They need to work right.
They need to work.
I mean, you can't just go with a half-assed type of thing, right?
No more URDs.
Yeah, for sure. So lots of testing needs to be done to get it right. And speaking about testing, you remember the Ingenuity, Robert? Do you remember that?
I do.
Now, do you want to maybe summarize a little bit what your memory was of Ingenuity?
Ingenuity was a small helicopter-like device that was sent to Mars. And it was dropped off by the rover part of the mission. Yeah. And they were just going to fly it around a little bit to see, hey, the proof of concept. This will work. And instead, it went for many days, months longer than it was supposed to. It picked up some rocks, if I remember, and flew almost to the line of sight horizon from the rover. So it did all kinds of great things. And then apparently it landed and got tipped over on its side. So when they cranked it up the next day, it shattered its rotors and never recovered. Yeah, so that was part of the Perseverance rover mission. And as you said, from an engineering point of view, it was only designed that probably if they were lucky to get 3 flights of the helicopter. Right. It's a helicopter / drone, whatever you want to call it. And the thing, of course, on Mars is that the pressure is like 1% what it is here on Earth. So the air is really, really, really thin. And so it's extremely difficult to fly a rotor-based device on the surface, to get it to lift off. Right. And one of the things you need, of course, is you need your rotor blades to be spinning really, really, really fast. And for the Ingenuity, and they end up doing, I think it was like 70-plus tests with the thing, 70 flights or so, before the last one had crashed and hit the ground too hard and broke the blades, essentially. And so one of the things they did is they kept the RPM to a low enough level that the speed of the rotor blades never exceeded the speed of sound. Right. But what they are experimenting with now in a chamber that simulates Martian environment with the low pressure are rotor blades for a future mission to Mars. And future is not that far off. It's only supposed to be a few years from now, where they actually had the rotor blades exceeding the speed of sound. In this case, Mach 1.08.
So
That's
the Mach
incredible.
value, the Mach 1 means the speed of
Just-
sound in the local environment you're in.
Just the engineering to make a material that will not shatter at that speed, at that rotational velocity. There's what we call a breakup velocity of things can spin up to that speed and no faster because they break up. And then there's the balancing issues. I mean, you think your tire, loses half a gram balancing weight on it, and you feel like you're being shaken, not stirred, going down the interstate. Just imagine at the speed of sound.
And of course, if you get the rotor blades to turn at such a high speed, that gives you more lifting capability.
Mm-hmm.
And I think they said something to the order of the tests that given the design of these rotor blades that they're testing here in this chamber, which you can see in the image, that just having it go from below the speed of sound, below Mach 1 to above Mach 1, gives them like a 30% increase in the amount of mass they can lift from the surface of Mars.
Right. Well, at those speeds, a little change will produce. I mean, the pressure gradient across the airfoil is related to the velocity. So, oh yeah.
So that's gonna be
This is
that's gonna be
impressive.
neat. And right now the plan in this Starfall type of mission, as they call it, and this was part of this redesign of the Artemis mission and everything else that came along with it, was to have a nuclear-powered rocket that would go to Mars. And then part of that would be dropping off the payloads, like 3 of these helicopter drone-like devices, to be independent. That is, they wouldn't rely on a ground station, like a lander, that they would be able to fly around the surface of Mars and just communicate with relay satellites in orbit around Mars itself. So you could go all over the place and not having to be in the line of sight with the lander or the rover in order to have that direct communication with Earth type of thing. So that's going to be a lot better. And you can imagine, if you develop these rovers to the point where you can make a lot of them, imagine a rover flying in Valles Marineris, the Grand Canyon of Mars.
I'm on board. Let's do it.
Wow. I mean, if you examine it, you can imagine the layering that's in the walls of the Valles Marineris.
I mean,
It'd be incredible.
I mean, I'm still kind of wanting a lander to go into the crater, the caldera of Olympus Mons.
Yes, you could do that.
You
You know
know?
what you need? Hummingbirds.
Oh, yeah. That'd
Right?
be even better.
You need these devices to act like hummingbirds.
Yeah.
So they could just stay there and they stick their little beaks, which is actually a probe, into the surface of different layers and then analyze the material. That's what you need. Hummingbirds.
Let's make the proposal, Wayne.
Mechanical hummingbirds. And you make them out of nanotechnology. We got a nano foundry right here
Right.
in our department. And so we can make nano devices. We'll make nano hummingbirds and put enough instrumentation on them that they're about the size of a real hummingbird here on Earth. And
Right.
away they go. And their little wings flapping away. And you know what, a hummingbird, how fast their wings go. You can design them enough that they could stay afloat in the atmosphere of Mars and go sample all of these different places.
I'm thinking of a great delivery method. You just drop off basically a spherical container, plunges down to the atmosphere till it's dense enough for them to work, opens up, just spills them out. They crank up, fly the rest of the way down themselves.
Wouldn't that be amazing?
I would love to see that.
And then you can explore, and then you have it like autonomous, right?
Right.
AI is running it. We use AI again today. AI is running them, so you don't need us to tell them where to go. They do all their own thing, right?
Right.
And they go to all these different locations on Mars that look interesting and send all those signals back to the satellite that's in orbit above them. And then all that of course, data gets transmitted back to Earth at some point. But that would be cool.
Absolutely.
In fact, not only could you do it for Mars, but you could also do it for a place like Titan.
Right?
And the only difference there is, well, there really is not much difference. Still going to be cold. In fact, Titan has a lot more pressure, and so it's going to be easier to keep things
rotors
alive.
don't have to turn as fast.
Yeah, so that could mean it's cheaper to build if you used it on Titan.
Right.
And that would be, I can't wait till the day we get the Dragonfly is going to go there right around 2030.
Yeah.
And land on Titan and fly around. Oh my God, that's going to be so cool. You get direct images of it. See what it's like on
See if
Titan.
we do have ethane and methane lakes and rivers.
It's going to be amazing.
Oh, yeah.
there's lots of good stuff coming, folks. You just got to hang on. Just got to eat healthy and be alive in the next 10 to 20 years to see a lot of this stuff. Now, speaking about developing things in a laboratory, NASA's also pushing away at trying to make better and better what we call ion propulsion engines. So there's a recent image of an experiment that was done, a test run, of a very powerful ion engine. In fact, the most powerful one that NASA ever built. This one uses lithium atoms. So you basically ionize lithium, give it a bit of a charge, and then you can have it being attracted to a sort of electrified plate or mesh, a screen if you like. And then these ions, the ones that don't hit the screen, goes right through the opening of the screen. And that provides the thrust that you need.
Yep. And remember, folks, a rocket works because it's ejecting mass out its back. It's conservation of momentum. It's not pushing against anything. It doesn't need to. But momentum is a conserved quantity. And so you throw some little lithium ions out the back of your rocket at, thousands, tens of thousands of miles per hour. Your rocket's going to go forward a little bit.
Right. For every action, there's an equal and opposite
reaction.
Newton's third law of motion.
Right.
And that's how the rocket works.
So, I love these ion engines because they have what we call a specific impulse, which is a measure of their efficiency. It's just off the charts compared to chemical rockets and everything. But the typical ones used now have a thrust in as far as the force it produces of about holding up a sheet of paper against Earth's gravity.
Yeah.
So they're not good for getting you off Earth, but they're amazing for pushing you along once you're out in space.
Exactly. In fact, if you think about the power that this engine can deliver, it's 120 kilowatts, which makes, and of course, that's just a number, and you're like, okay, what does that even mean? It actually means that this engine is 25 times more powerful than the one that's currently being used on the mission to go to Psyche, the asteroid. It's in the main belt. And that's due to arrive there in July of 2029. Right. So we only have about 3 years to go before that happens. So it's this engine then that's being tested on the ground. It's 25 times powerful than the most powerful one that NASA currently has flying.
So it's 25 sheets of paper.
In fact, reading up on this, they're actually going to try to extend it until we get to megawatt type of power.
Oh, heck yeah.
So that's what they're developing now. So eventually, maybe 10, 20 years from now, we're going to have, megawatt type of ion propulsion engines available to fly around the solar system.
That's when we start talking about interstellar probes.
That's the interesting thing.
Because that level of engine, between stars, you've got plenty of time to use a small amount of thrust to build up just an incredible velocity. And so, we get up to those levels. We have to start thinking about that.
I'd make the case that NASA should be doing mostly that kind of stuff. That is developing advanced propulsion and, more of this sort of nitty-gritty grunge type work, like going to the moon on normal chemical rocket stuff. That should all be developed and built by private companies, and NASA just pays for their service.
Right. NASA should be a science and research entity.
R&D.
Yeah.
Right at the forefront.
Absolutely.
And ultimately trying to come up with vehicles that will, be at a point where we can launch them to other stars.
Right.
And not only do we explore the solar system, let's explore our galaxy.
Mm-hmm.
And it might take 200 years to get there in terms of developing the technology, but if we don't start now,
we'll never get there.
It's going to be more than 200 years.
Right.
So at some point, we should be doing these things. And anyways, but I'm not in control of NASA, and of course, the American taxpayers are the ones that got to pay for all this stuff.
Yeah.
So they need to
at the same
agree.
time, let's climb Everest. Why? Because it's there.
Yes, and we can certainly multitask. We don't just do Artemis. We don't just do this kind of work. We try to do everything that we can.
Right.
And that keeps us all motivated too.
Yep.
Now, the other thing, of course, that we talked about already today was the delay in the Artemis project, and this is kind of a headline from space.com, just kind of, if you like, agreeing to that the Artemis 3 right now mission has been pushed to 2027. There's so much politics involved when you start talking about the administration of NASA It's a political position, obviously.
Yeah.
And what happens is initially they were talking about early 2027 Artemis 3 will launch, and that's the test, remember, of one or more of the landers. So if only one of them is available from one of the companies, they'll test that. If two of them happen to be available, they'll test both of them in low Earth orbit. And it's a smart thing to do, because if something goes wrong, you can get back fast.
Right.
So you don't want to be waiting 3 or 4 days to transit the distance from Earth to the moon when you have a major problem. Just think of Apollo 13 if you want to, if you want to consider what that's like. So now the time frame, because the administrator just said it. Oh yeah, when we get Artemis 3, which will be late 20. It's like he didn't even make an announcement. He just changed it.
Yep.
And it's like he knows more, of course, the inside information than what anyone else would know. So he said, oh, yeah, the Artemis 3 will launch late 27. Well, I thought you said it was early 27 like 6 weeks ago. Now it's late. So things are changing, and that's because, and it's not a surprise to us because that's the change in the time schedule of getting these landers available. They're not ready. And it's not unusual. Back in the Apollo project, the lunar module wasn't ready in time as they thought. That's why Apollo 8 went around the moon and, in orbit for a while and then came back, because the lander wasn't ready to go.
Right.
They didn't have that till Apollo 9.
At the same time, I will argue, and don't get me wrong, throwing money at a problem is not always the best response or answer, but that was what was going on during the Apollo era, is money was being thrown at the project, get this done. So, yeah.
And one of the main problems they had with the lunar module back in the Apollo days is they had to keep the mass of the vehicle under a certain limit.
Right.
And you had to cut. They thought, okay, eventually you, as an engineer, right, you build this beautiful machine.
Yeah.
And you include like seats for the commander and the lunar module pilot, right? You have all of this stuff. But the seats they have a certain amount of mass, right? Mm-hmm. So it was too much, so they had to throw them out. So they left them standing.
Right.
Looking out the windows. Well, the windows were too big.
And too thick.
Because they're too
heavy.
Massive, so they had to shrink down. Do you really need the windows this big? Could you get away with making them a heck of a lot smaller in terms of being able to see out? And they do all these and then do the walls of the vehicle need to be that thick? Mm-hmm. We are in the vacuum of space, and we're under this low. I forget now what was the pressure inside the lunar module. Something tells me it was on the order of like 4.5 pounds per square inch or something like that order. Do you really need to have thick walls? Can we trim the thickness of the walls of the vehicle?
And so you end up with foil.
Yeah, you have paper thin walls that if you're not careful, you could put your elbow out through the side maybe, right? So that's a problem. So you do all these reduction in what you had initially, trying to lower the mass to the point where now it can fly on the Saturn V and the vehicle and do the things that it's supposed to do. And that took a lot of time.
Yep.
And of course the engine you need something that's going to work. You don't want to be on the moon and you go, okay, 3, 2, 1, ignition. You push a button or the computer lights it up and you get nothing. It's like, uh-oh. So it has to be extremely, not just reliable, but 100% reliable.
Right.
And so all of those things must be done. And that's a lot of R&D that had to be done and done right. So you can't skimp on that. So once again, it's not surprising then that there's a bit of a delay here. And in fact, I would recommend, if I was NASA administrator, I would recommend you don't fly these missions until you're 100%, or at least as much as possible, sure that you've done things right.
Yep.
Because if you do things wrong,
you're reading the other letter.
Yeah, not only do you kill people, but the program is probably canceled.
Yeah.
So it's worth it to take the time to do it right.
For those of you who don't know, check into Nixon. He had another letter prepared to read. So, yeah, you don't want to be in the position of having to read the other letter.
Exactly. Now, Robert, this is the favorite or best time of the podcast for you because it is a time to go into statistics. There's two things in life, Robert. Mm-hmm. There's statistics and damn statistics, as they say.
And most of the time, most people are aware of working with the damn statistics.
Now, Robert, do you want to explain to everybody what we're seeing here?
Yeah. Basically, you're seeing the dreaded bell curve, the Gaussian curve, that if things are uncorrelated and completely random, you are going to get this result. Now, the neat things are you can change the width of that point. That center line is the median. If you start having it being more to one side than the other, you get into things like skew and kurtosis. But in a perfect shape, that center line is the median, so it's what most of us think of as an average. And then these sigmas that we've been talking about and throwing about for episodes now, we're talking about the standard of deviation, which starts getting into just how wide that bell is. And so it also starts telling you how many of your measurements fall within that range of sigma around that median. And so, we throw around 5 sigma. Well, the graphic shows you that that's 99.99994% of the results are within 5 sigma. So if you're that accurate or you're getting that good of the detection, you've covered most of your error space. Okay? But results will be reported as 5 sigma, then plus or minus, and you'll give a value of that sigma, what it means, absolutely. And so that starts telling you how narrow that peak is and just things like that. And all of a sudden, because, you could be 5 sigma, and if your peak is well-rounded and real broad and flat, well, that's not a terribly good result either. So what we really ideally want is, what we really want would be a lovely Dirac delta function where everything is right on that mean, and the sigma width is 0, but that's not going to happen in the real world. So
and the other thing, Sue, if you see something new, you want it far away from that central line, that mean. And so in particle physics, for example, and most of other science, let's say you detected, or you think you detected, a new particle.
Right.
And they wait until the measurement of the new particle is at least 5 sigma away from the 0th, if you like, of non-existence of the particle.
Right.
It's kind of one way to think about it. And by the time your measurements, if they're precise enough, that says, this is a 5 sigma detection, that means there's like a 1 in 3.2 million chance that it's a random fluke, that you get a signal deviated away from the average or the 0 marker, if you like.
Right. It gets into the whole scientific method, your null hypothesis, your 0 hypothesis. So it's kind of the inverse of that bell curve. We want it away from that central value, because that central value means, hey, we didn't find anything.
Yeah, so let's say your central value is 100. Your average value is 100. And if you find a measurement and it comes out to be 101, but the uncertainty on that measurement is plus or minus 50.
You didn't find anything.
You didn't find anything. That overlaps with 100.
Right.
And there's no significant detection there at all. But if you find that your measurement of 101, with uncertainty of 0.0001, that is many, many, many sigma away from the value of 100. So that is a real detection that there's something there.
And we won't base that on one detection usually. I mean, it's usually, especially like at the LHC or other things, it's millions of detections that go into that. So,
and of course, in science, you want to confirm somebody else's measurement, because even though they may report it as 5 sigma or more, and therefore it's a real thing, how do you know there's not a hidden systematic error or bias, if you like, in the measurement? That is, their measuring device could be not calibrated properly, or their technique or method that they use is flawed in some way.
Right.
And you go and run a similar experiment and you find, no, there is no 5 sigma detection here. I don't get anything that's at that sort of confidence level. Then you know there's something else. And so what happens in real science, if you like, is that you get multiple measurements done by different types of groups of people, independent of each other. And if they all sort of converge to the same answer, then you have very high confidence that's a real thing.
Right.
But if no one finds it, just you,
Well, that's a you problem.
Chances are something false. Amy, just to kind of think about it, and we talked about it in the last podcast, there was the group in Italy, for example, that reported with the measurements of neutrinos that neutrinos were traveling faster than the speed of light.
Right.
Now, if you abide by the special theory of relativity, that should not happen. And they published a paper saying so and said, this is what we found. We don't know what's wrong. We've checked everything that we could think of. Could you please help us with this? Could you look at it and see where we messed up?
See where we messed up. Right.
And, of course, nobody found anything because it turned out to be actual faulty cable hooking up one of their instruments to some other device or whatever that was causing this, speeds to be greater than the speed of light.
I remember it because I remember being exasperated with that report because the mainstream media just ran with it. Hey, we've discovered something going faster than light. And anybody in the field was going, that's not what they reported.
Yeah. So you always have to be careful. And, of course, when they swapped out and put in the cable that actually was functioning properly, the measurement went away.
Right.
The neutrinos were traveling less than the speed of light because
they
they have a mass and they can't travel the speed of light.
Right.
But this whole statistical thing, we can use that now by the next story. And this is a measurement that was done recently by the compact muon solenoid, the CMS detector, which is part of the Large Hadron Collider over in CERN in Europe. Mm-hmm. And what they did is come up with a very precise measurement of what we call a measurement of the mass of what we call the W boson.
Right.
Now, for those who are not familiar, there are sort of four fundamental forces of nature. The weakest one by far is gravity. There's the electromagnetic force, which we're used to. You think of that as electricity. That's what prevents us from falling through the floor towards the center of the Earth due to the pull of gravity.
Because atoms are empty space, so it's the repulsion of the electrons.
And then there is the strong nuclear force. That's responsible, for example, to keep protons together inside the nucleus of an atom. For example, let's say carbon. Okay. Mm-hmm. And then there's the weak nuclear force that's responsible for radioactive decay, for example.
Right.
Now, for the weak nuclear force, it has what they call in particle physics a carrier force. Think of you accumulating packages from Amazon. Somebody has to deliver those packages from Amazon to your doorstep. Right. So the carrier, Amazon Prime vehicle, right, the carrier in this case is actually three different particles. Mm-hmm. There is the Z boson, which has no electric charge. And then there is the negative and positive W boson. So there's a negative flavor, if you like, and a positive flavor. And all of this stuff, interesting enough, was predicted when people like Steven Weinberg came up with the electroweak theory, the unification of electromagnetism with the weak nuclear force. They predicted the existence of these particles. People did experiments, and lo and behold, there they were. So Steven Weinberg, Sheldon Glashow, and Abdus-Salam, they get the Nobel Prize in Physics for the electroweak theory.
And I'm going to bring up something because you mentioned something that a lot of people have trouble understanding and accepting because it's not their experience with the world. But you said that gravity by far is much weaker than any of the other three. How much weaker? Well, the next strongest is the electromagnetic force. And
the strong nuclear force.
Well, I mean,
in terms of
from
going
gravity,
up in strength, yes,
the strength
so
goes
it'd be the
up
weak
to the
nuclear force.
So if you think about it, our experiences with the whole Earth, that's a strong gravity field. Yeah, really, your refrigerator magnet will stick to your refrigerator and not be pulled down by the whole Earth.
Yeah,
electromagnetism is much, much stronger.
And another way you can think about it, right? If you take two particles, two protons or two electrons,
right,
and they have a mass, so then you can easily calculate what is the gravitational force of attraction between those two particles. And let's say those two particles you select to have the same charge, so they're going to repel, move away from each other. You can then calculate from electricity and magnetism what is that repulsive force. And depending on which object you select, you're talking about differences of 1 followed by over 40 zeros stronger than the gravitational force.
So, yeah, folks, I know gravity seems strong, but gravity is puny compared to the other three.
But it doesn't help, though, when you fall down an elevator shaft.
Oh, shoot, no. But
Don't worry, gravity is weak.
Yeah, I will still argue that, as we mentioned, what keeps you from falling to the center of the Earth, because atoms are empty space, is electromagnetism.
Yeah.
So it really isn't the gravity that causes the problem. It's the sudden stop, the electromagnetism at the end.
Exactly. Yeah, it's the interaction of the electron cloud and the atoms.
Yeah.
That's the real issue there. So anyways, so with this detection, if we go to the next slide, you can actually see a comparison of what has been detected in the recent past to what had just come out now, essentially. And the sort of vertical band you see in the middle, that's the prediction of the mass of the W boson from the standard model of particle physics, as we say. Mm-hmm. And as scientists, we are looking for things that don't agree with the standard model, because if we do every measurement now on for the rest of humanity, and every measurement we do is consistent with the standard model particle physics, that is boring. What we want to do is find something that's beyond the standard model.
Yeah.
And things that include, for example, the detection maybe of dark matter particles and so on and so forth that are not incorporated within that standard model. So we want to find something beyond that.
Yeah, you don't make a career in science by agreeing with everybody else. You do it by disagreeing, by saying, hey, this is new.
Now, on the plot you see here on the horizontal axis is the energy, which is, E equals mc squared. So you could take a mass and convert that to energy. The speed of light squared is just that conversion factor, so it's easy to do. And you actually see one that I pointed out to. It's a measurement that was published back a few years ago, not that long ago, that illustrates that they thought that the W mass was about 7 sigma away from the value predicted from the standard model.
That would be new physics.
7 sigma. Now, the error bars that you see there, so you have the black point in the middle of the different measurements. There are 6 different measurements. That's the value. And then the bar that goes, horizontal bar to either side, that's the extent of 1 sigma of the error bars, we say, the uncertainty in that measurement. So if you take half of the total bar, so go from the black point to the left side where it ends, that 7 sigma measurement, there are roughly 7 of those lengths before you get to the middle of that vertical band that runs up and down. So that makes it a 7 sigma detection, which is well beyond 5 sigma, and therefore one would expect it is a nice, robust detection that it's real. But like we've already said, how do we know there's some inherent bias or some systematic problems that we're not taking into consideration? So that uncertainty might be a lot larger than what we think it is, or there's just something wrong with the equipment or measurement.
Right. And so other people check it. What was the result?
So the result is the one you see in the very bottom point there that's in red. And notice that the dot is right on the edge of that band. In fact, it is less than 1 sigma away from the predicted value from the standard model.
Right.
So these new measurements, very precise measurement. Why do I say that? Because the error bars are the smallest of the data points you see there, and the smaller the error bars, the more precise the measurements. They agree totally with the prediction from the standard model.
Right. So somebody messed something up with that other experiment.
Very interesting results.
Oh, yeah.
And like I said, it's always nice to show what the Large Hadron Collider is providing, since there's so much focus initially on the discovery of the Higgs boson that people wonder, what have you done for me recently? And this is part of that, going down that tree of trying to test things and compare it to theory, to looking for, because you want something that's different. Because if you find something for sure that doesn't agree with the theory, then obviously that theory needs to be modified. It's not perfect.
Right.
And so changes need to happen.
And you get to a better theory. So
exactly. And that's the way you push the frontier of discovery and knowledge in science. Now, for those of you who are interested in science or any other higher education programs, one of the things you can do is come to the University of North Dakota. Yeah. We have a lot of interesting stuff that's going on. In fact, if you come today, especially at the end where Whitmer Hall, where the physics and astrophysics department is located, right across the street from us, you see the construction of what's going to be a really beautiful, brand new STEM building.
Right.
And so there are lots of amazing things happening on campus. So we are not stagnant. We are trying to make things better all of the time.
Right.
Now, if you're
Yeah.
trying to make your education better all of the time, things you can do include taking online classes.
Right.
And those you can take from anywhere in the world or universe, as long as you have a connection somehow, right? I advise you to take it from somewhere on Earth because it's a little better, a little
Yeah, it's a
faster,
little better signal.
a little faster to
Yeah,
get your
yeah.
information back and forth. But of course, that doesn't prevent you from taking classes online, and we have lots of interesting things going on. Too numerous to mention in the short time we have available now.
Right.
But trust me, bro, we have a lot of things happening here, a lot of good things happening on campus. And I just would say, if you're nearby or you happen to visit, come see us.
Come see us.
Drop down, see what's going on at the University of North Dakota here in beautiful Grand Forks.
Indeed.
Now, the other thing, as you know, at the end of our podcast,
You leave
is
us
we
with a quote.
always bring up a
quote?
quote.
A quote.
And I've thought about it. It's like, we just finished talking about the Large Hadron Collider and particle physics. Let's have something from a particle physicist.
So Higgs, Mr. Higgs?
Nope. Good
No?
guess, though.
Okay.
Isidore. That's the first formal name of this person. You know who it is?
Nope. Can't say as I do.
Okay, the second, Isaac.
Isidore Isaac.
I
don't know.
Robbie. R-A-B-I. Robbie, who was involved in a lot of discoveries and early work that was done in particle physics
Okay.
and in nuclear physics and so on. An extremely important person. In fact, if I'm not mistaken, like the medical devices, a lot of them that were developed by him, or at least the theoretical part of stuff.
Right.
And a good quote from him, a well-known quote from him, is what he said about the discovery in 1936. So he passed away in 1988, born in 1898. So he
Wow.
lived in the in fact, in the exciting time of the development of quantum mechanics, he was in his early 20s. How perfect of a time was that?
Beautiful.
To be at the right time in your life where you can contribute to
Yep.
a lot of this stuff, a lot of this development. Very, very cool in that sense. And when the discovery of the muon, which is if you like, a heavier version of the electron, it's about 200 times its mass. When that was discovered in 1936, that was not expected. Nobody thought that should
Nope.
exist.
Right.
And so he's famous for saying, "Who ordered that?" Now, if you like our podcast, please remember to give us a thumbs up, subscribe if you haven't subscribed, and remember, we'll see you 2 weeks from today. Thank you for watching.
Bye, folks.